Yesterday we stopped here. It's about charge quantized. Charge is quantized, and it's nothing special. You should have learned this in chemistry class, so that you should be able to know that the electron has a negative charge E, which is 1.6 times 10 to minus 19 Coulomb, and proton has the same amount but a positive charge. The neutron have the same mass, more or less the same mass with a proton, and it is electrically neutral. So these three kinds of particles to form all the elements on the periodic table. So this is nothing special, I think. So it's something like it tells you you can have 10e minus 6e, but you cannot have 3.57e, which means charge is quantized. You can only count one charge, two charge, or one negative charge, two negative charge, and so on. You cannot have 0.5 charge. So this one is easy, I think. So now we have sphere A has a charge of minus 50e, and sphere B has a charge of plus 20e. So when the sphere are made of conductor material and are identical in size, if the sphere then touch, what is the resulting charge on sphere A? On sphere A. Okay. Anyone can tell me? We have this one minus 50e, this one 20e. The size are more or less the same, are actually identical. And then we use a very tiny wire to connect them together. So what will be the charge on sphere A? Yes, of course. Negative 15e. Actually, it is just minus 50 plus 20, and then divide by 2, which means the overall charge is minus 30, and then it share to A and B. The point they are in the same size means that they share the same amount of charge. So this is easy, and the next one actually is not. This is not difficult, but this sample problem is just to tell you another story. So let's just calculate this quickly. So for this one, it tells you that the nucleus of an iron atoms has a radius about 4 times 10 to minus 15 meter femtometer. Very, very, very tiny. So and contains 26 protons. What is the magnitude of the repulsive electrostatic force between two protons that are separated by this distance? So actually, you only need to substitute the number into the Coulomb's law, and then you get the force. So actually, it is just F equals K times. It tells you that it is two protons, which means plus E. So it should be E times E, which is E squared, and then over this distance, 4 times 10 to minus 15, which is just an approximation. It tells you that this is the iron atom, so it should have some electron go around it, not necessarily circular, but you can imagine there will be some electron going around the nucleus, and the radius of the neutron of the iron atom is this one, 4 times 10 to minus 15 meter. So it asks, for example, there should be some proton and neutron inside. So maybe a proton is here, a proton is here. So there should be some repulsive force because they are all positive charge. So this force should be something like this. And actually you can just substitute the numbers, 8.99 times 10 to 9 times 1.6 times 10 to minus 19, and this one 4 square, and 4 times 10 to minus 15 square. You just substitute all the numbers, and then you get the force something like 14 Newton, which is quite large. Which means that there is a force repelling them. The force should be so large like this, So you just keep this in mind. And the question B, what is the magnitude of the gravitational force between those same two protons? So actually, I suppose you should have learned it in the mechanics, which means that the gravitational force, which is gmm square, which is both of them are mp square, r square. Actually, it's just a story. You don't really need to remember this gravitational force for your quiz. And so the big G, capital G, is 6.67 times 10 to minus 11, and then MP is 1.67 times 10 to minus 27 kilograms, and then the quantity square, and then over the same amount, 4 times 10 to minus 15 squared, minus something like this. The R will be the same, and this is the mass of a proton, and this is the constant G in the gravitational force. So the answer should be 1.2 times 10 to minus 35 Newton. That would be very strange. Because these forces are attracting the two protons. If you just ignore all the others and imagine the protons, there are two protons here. Two protons, then it has a positive charge E, so that the electromagnetic force repelling them, because they are both positive charge, so that they're repelling by 14 Newton, if you still remember. But this one is the gravitational force. They attract it. But this is actually really, really small. 1.2 times 10 to minus 35 Newton. So they should be, the atom should collapse, should break, right? So this is what, which means that if you only have the proton, neutron, and electron, something like that, we cannot really explain why the atom would be a stable element. So for the physician, they will try to have a model to imagine how to make it work. Actually, you don't really need to remember that. It's just a story to tell. it's very hardcore physics stuff. I only know it a bit. So you can regard it as a story. I will not ask you in the exam. So don't need to worry about it. Actually, the story is like this. We have the how can I? Oh, sorry. How can I? Yeah, this is the standard model of the elementary particle, or in Chinese, 粒子物理标准模型. So you may have heard what is quark, oh, and then the physician will tell you that a proton is actually some up quarks plus some down quarks, and then it forms the protons. And then for the neutron, it is a number of up from plus another number of down quarks, and then it forms the neutron. So they will tell you that if you further break the proton neutron, it has smaller and more basic element to form the universe. And actually, we have something called the gluon. In Cantonese, it's called 高级. So it's something like the glue to make them together, because we cannot really explain. The two forces cannot cancel each other, so that they should break, but they do not. So here, the physician tried to explain it like this, and the quarks is something like it has half spin, and sorry, I mean the fermion. The fermion is having half spin, and the boson is spin is 1, but actually we don't really need to know actually. So it's just a simple story. The physician will consider the world like this. They will make some assumption to explain some of the phenomenon. But if what they derive contradict with some further experiment, they will try to refine the theory, and then they will make maybe some complicated theory, which is difficult to understand. So the next topic is about charges conserved. Actually, just as the previous example, just as this one, the charge is conserved, which means that originally, before you connect the sphere A and sphere B, yes, minus 50e, 20e, so that the total charge is minus 30e. And after you use a small wire to connect them, the total charge is still negative 30e, so that you cannot create a charge or brand using a charge. But yeah, or still also for the physician, they will have some difficult theory. They say that there are antiparticles. So we have a electron, and this is called a positron, which is a 正电子. So that when the electron and the positron are interact with each other, then they will vanish and then become some energy. 它们会湮灭，然后变成一些gamma ray， 就变成一堆能量。So later in this semester, you see this again. Actually, the gamma ray is something like a high energy particle for very low frequency, for something like RF. You use it to transmit signal, microwave transmit signal. You use a Wi-Fi, 3G, 4G, 5G. 5G may be somehow here, maybe using 30 gigahertz rather than a few gigahertz. Yeah, the infrared 红外线 ultraviolet 紫外线 is somehow lying here. So all of them are electromagnetic wave, and then I think you learned it in chapter 33. I'll try to tell you how to solve the Maxwell equation, and then you have the wave equation somehow like this, and then solve the differential equation. So you get the answer for the EM wave. So here is an additional example. Well, this is something like this. We have particle 1 and 2 have charge 20 microcoulomb, 20 microcoulomb each. And a hair at the separation distance d equals 1.5 meter. What is the magnitude of the electrostatic force on particle 1 due to particle 2? Magnitude of the electrostatic force. So actually, you only need to yeah. So actually F12 is nothing but K Q1 Q2 R squared, or D squared. Here is D, so it should be D squared. And we substitute the number, so K is 8.99 times 10 to 9. And Q1, Q2 is above 20 mu C. Mu is 10 to minus 6, 10 to minus 6 square. And then D is 1.5. So the answer should be 1.6 Newton, nothing special. Why do I include such a stupid example here? So for the next one, particle 3 of charge. Well, maybe I just skip it. I think it's too stupid. Okay. Huh? 差不多. Okay. Yeah, it's just something like the vector sum. So it should be very, very simple. So if you don't really know, you can come to ask me. So I think it is too stupid to repeat it here. So let's come to the next one. So 3 identical conducting spheres initially have following charges. A is 4Q, B is minus 6Q, C is 0. So A and B are fixed in place with a center-to-center separation that is much larger than the sphere. Yeah. So 2 experiments conduct experiment. In experiment 1, sphere Z is touched to sphere A and then separate to sphere B. Then it is removed. So what is the ratio? And there's still experiment 2. So but let us explain experiment 1 first. So actually we have, so there are many words, so we can try to summarize it like this. So we have A, B, and C sphere. We have 3 spheres. So for experiment 1, what did we, initially we have 4Q for A. So we have 4Q of A, minus 6Q for sphere B, and 0 for sphere Z. So just show it here. And so in experiment 1, sphere C is touched to sphere A. Is touched to sphere A. Then separate. So that after these steps, it will be somehow like 2Q, 2Q, because they share the same amount of charge. So we have 4Q plus 0 and then divide by 2. So both will have 2Q after touching. So sphere B doesn't change, so you still have a minus 6Q. And then next, sphere B, and then touch sphere B, then it is removed. Still, sphere C to touch sphere B, because your English should be good enough. Sphere C to touch sphere A, then separate to touch, which means the subject for the second one is ignored. So actually sphere C will touch sphere B again. So sphere A doesn't change. And then for B and C, we have totally minus 6 plus 2Q. So we have minus 4Q. So at the end, we'll have minus 2Q, minus 2Q. So for experiment 2, maybe I just add a additional blank slice here. Otherwise, I don't have enough space. So for experiment 2, still the initial state is somehow like 4Q minus 6Q and 0. So what we do here is sphere Z touch sphere B first, and then separate, and then to touch sphere A, and then this is removed. So the order changes. So first time B and C touch. So A doesn't change, and then B and C become minus 3Q. Minus 3Q. And then they separate, and then sphere C touch sphere A. AC touch each other. So that's minus 3Q here. And then A and C have totally Q, so both will have half of Q in the end. So this question is to ask you the ratio of the electrostatic force between A and B at the end of experiment 2 to then at the end of experiment 1. So actually the electrostatic force for sphere 2, and sphere 1 will be actually sphere A and B. For experiment 2, it is half Q and minus 3Q. So half Q minus 3q multiply together, and then dy by a distance d squared. And then for experiment 1, both have A have 2q and B have negative 2q. So k times 2q negative 2q over d squared. So the answer will be 0.375. 0.375. So actually this is not difficult either, but you only need to read the English. So actually this is the end of chapter 21.